Hi, this is the second lesson on eigenvalues and eigenvectors. Can I recommend that you watch the first lesson so that you can see where the ideas are coming from? In this lesson we're going to look at a slightly different scenario. In the last lesson we looked at two-way stretches and how we can use eigenvalues and eigenvectors to help us describe two-way stretches. We're going to have a look at a different scenario in this lesson. I'm going to start by writing what hopefully will be a familiar idea for you. I'm going to write down a transformation matrix like so. Now hopefully you can recognize that this is going to produce a shear. Now if you're not sure what a shear is, we'll pop over to Autograph and I'll let you have a look. Okay, so I have a rectangle over here and I'm going to carry out the transformation that we just looked at a second ago. Okay, so I've got 1, 2, 0, 1 and what we said is that this is a shear. If I press OK, and we can see that what has happened is the points on the y-axis have stayed where they are, and the other points have kind of slanted over to turn this rectangle into a parallelogram, and the key movement is this one here. The point 3, 0 has shifted to the point 3, 6, and if that had have been 4, 0, that has shifted to 4, 8. Okay, right, so we can see the effect of this. What I'm going to do is I'm going to delete a couple of these points and I'm going to turn this into a position vector. So I'm going to leave one of the points fixed at 0, 0, and this is going to be a point that I can move around to give me different position vectors. Okay. And in the last lesson what we did is we moved this point around and we were looking for what we called eigenvectors, which is where a point maps back onto itself somewhere further along a line. And if I move this around to try and find a eigenvectors, we can see that we don't seem to be getting anywhere just yet, but there we go, we seem to have got somewhere here. And actually what's happened here, the point seems to have mapped back onto itself. So this here looks like it's an eigenvector in the direction 0, 1. The eigenvalue here, because the factor which is kind of stretching along here is just 1, because it's mapping straight back onto itself. Okay, so this here, instead of being an invariant line, we can be a little bit more specific. This is actually a line of invariant points. Any point along this line is going to map back onto itself, so it's a line of invariant points. Let's see if we can find any other invariant lines. And here we're on the same line again, and actually it looks like we've only got, I can't seem to find another invariant line. Okay, so this looks like we've only got one line of invariant points. Okay, and in fact that's going to be the case with any shear. If I have a shear, I'm not going to have, if we can go back to this being, go back to this being a rectangle, we can see that any point along this line will map back onto itself, and that's the only place where the points are going to map back onto themselves. There isn't going to be any other line of invariant points, and in fact there isn't going to be any other invariant lines, because everything is kind of slanting away from the rest of this rectangle. Okay, so we'll go back and we'll see if we can jot some of this down. Okay, so we can describe this now as a shear that's going to be, and it shears in a direction that's parallel to the y-axis. Parallel to y-axis. Okay, and the other thing when we do is when we're describing a shear is we say where one of the points map to. So I'm going to say that the point 1, 0, and if I multiply this transformation matrix by 1, 0, it's going to map to and it's going to map to 1, 2. Okay, so the point 1, 0 maps to 1, 2. And that's our full description of a shear. Now the other thing worth noting is that the determinant of this is going to be 1 take away 0, which is just 1. So that tells us that the area is invariant, which is another clue to tell us that this is going to be a shear. Right. What we had here though is we had a shear that was parallel to the y-axis. I could have a shear that's parallel to the x-axis, and that would be written where we've still got our identity matrix going, well, we've got our leading diagonal, sorry, I should say, as 1, 1 there, and this time I'm going to make this one 0, and this one could be 2 or 3 or anything that's non 1 and non 0, and then that again is going to give us a shear, but this time it's going to be parallel to the x-axis. Okay, and I'll write down the description of this one. So this one is a shear parallel to the x-axis, and this time we're going to say that the point 0, 1, remember 1, 0 this time is just going to be invariant, so 0, 1 is going to map to 3, 1. Okay, so now these were recognizable because one of them was a shear parallel to the y-axis and one of them was a shear parallel to the x-axis. But what about if our shear was parallel to something that wasn't the y-axis or the x-axis? So this is the y-axis, which is 1, 0, 1. That describes the direction of the y-axis, and this here, the direction of the x-axis was 1, 0. But what if we wanted a shear that was, or our transformation was a shear that was in the direction 1, 1 or 1, 2 or negative 1, 5? How would we be able to recognize that? So this is now the idea that we're going to explore. I'm going to write down a transformation matrix, and we're going to call it M, and we're going to say that M is equal to negative 1, negative 2, 2, 3. Okay, so what we're going to do first of all is we're going to have a look at this on autograph, and we're going to get a feel for what's going on. Okay, so I'm going to turn this into a position vector first of all. So we're going to fix the 0, 0 again, and this is going to be my flexible point that I can move around to give me different position vectors. And I'm going to apply my transformation matrix to this, and that's going to be negative 1, negative 2, 2, 3. Okay, and there you go, and that's ended up there. Now I'm going to move this point around and see if I can find any eigenvectors anywhere. Don't seem to be able to find any just yet. Whoops, and there we go, we've found one, and there seems to be an eigenvector at 1, 1, and because the points are mapping back onto themselves, the eigenvalue is going to be 1, which tells me that this is going to be a line of invariant points, or the points along the line 1, 1 seem to be mapping back onto themselves. Okay, great. I'm going to see if there's any more eigenvectors anywhere. See if I can spot any more. That seems to not be happening for me at the moment. There we go, and that's the same one again. We've still got the direction 1, 1. This is -1, -1, so that's not a different one. And there you go. I seem to only have one eigenvector that's there. Okay, so what I'm going to do now is, because I've only got one eigenvector and it has got an eigenvalue of 1, then that's telling me that this is going to be a shear. If I turn this back into a rectangle, I can see, well, it's difficult to see, but there's actually a shear that's in the direction 1, 1. To try and make it a little bit more obvious that that's what this is, I'm going to see if I can turn this into a different shape. Okay, and hopefully it's a little bit clearer here, that I've got my line of invariant points along here, along 1, 1, and I've kind of got my rectangle here that's kind of being slanted along in the direction, so parallel to the line 1, 1. Okay, what we're going to do now is we're going to go back to looking at this algebraically, and we're going to see if we can find what the eigenvalues are and the eigenvectors are algebraically, and see how we could use that to describe the transformation. Okay, so if we just jot down what this transformation is first of all. This is from our own investigation, so we decided that this was a shear parallel to, and it was in the direction 1, 1. And we decided, well, we can have a look at the point 1, 2. If I multiply this transformation matrix by 1, 2, that maps to 3, 4. Okay, so we're saying that 1, 1 maps to 1, 1, so that's invariant, and that's why it's a shear parallel to 1, 1, and 1, 2 maps to 3, 4. Okay, so what we're now going to do is we're going to have a look at analysing this algebraically to see if we can come up with this same solution without having to look at the graphs. Okay, so I'm going to start off by saying that I know that if I've got A minus lambda, B, C, D minus lambda, oops. Why I want that to be equal to 0, 0. Okay, and this is the equation that we want to solve. So I'm going to substitute in my values here. So Okay, and if you remember back to the last lesson, we don't want the determinant of this to be anything but 0. Okay, so we want this to be singular. So I'm now going to make the determinant of this equal to 0, and that's going to give me my characteristic equation, and hopefully I will be able to use that to work out what my eigenvalues are. Okay, made a bit of a mess of that. Okay, 3 minus lambda, and I want that to be equal to 0. Yes, so that's my determinant. I want that to be equal to 0. So if I just multiply that out, take away -4, so plus 4 is equal to 0, and that's going to give me lambda squared, and I've got take away 3 lambda plus lambda, so take away 2 lambda, and that's -3 plus 4, so that's going to be plus 1 is equal to 0, and this here is okay, so that tells me that I've got a single eigenvalue which is going to be equal to 1, which is what we expected from what we did before. Now I've just tidied this up a little bit so we can see a little bit more clearly what's gone on. Now the important thing here is that we have found a single eigenvalue which is equal to 1, and that tells me that there's a single line of invariant points. And because that's the case, and it is a single line, that tells me that it must be a shear. Okay, what we're now going to have a look at is finding the direction that our shear is going in. So I'm now going to use this lambda is equal to 1, and I'm going to use this equation here. And because I know what lambda is, I should now be able to go on to solve this equation to find out what my eigenvalues are. So over here, and I'm just going to, so we've got I've chosen the wrong equation now. We're going to use, oops, that's what I meant to highlight. Okay, so over here I'm going to say -1 take away 1 is -2. I've got 2, I've got -2, and I've got 3 subtract 1, which is 2. Okay, so that means that we want -2x plus 2y equals 0, and we want -2x plus 2y equals 0. Yes, so I'm just timesing that out. So that tells me that one possible eigenvector could be when x is equal to 1 to make that -2, and y equal to 1 to make that 2, and I add those together and I get 0. So my eigenvalue, which I'm going to call E, is going to be equal to 1, 1. And remember, it can be any multiple of 1, 1, so it could have been 2, 2, it could have been 5, 5, or -7, -7. It could have been anything, as long as the top and bottom component were the same as each other. Okay, so using that information now, I can decide, well, I know it's a shear because lambda is equal to 1, and I could have also have spotted earlier that the determinant of this is 1, so the area is invariant. -3 take away -4 is 1. Okay, so so that tells me that it's going to be a shear in the direction 1, 1, which is basically what we found here. I could also go on to find out where one of the points maps to, so that I can give a full description of the transformation. Okay, so just to recap on what's happened so far in this lesson and the last. In the last lesson we found that there were two distinct eigenvalues, and that told us that it was a stretch in two different directions, so it was a two-way stretch. In this lesson we found a single eigenvector, a single eigenvalue that was 1, and that told us that it was going to be a shear. In the next lesson we're going to have a look at a slightly different scenario, and then we're going to move on to having a look at transformations in 3 dimensions. Okay, thanks very much for joining me. I'll see you again soon.